Welcome back to the deep dive. Today, we're jumping straight into what is, I think, one of the biggest bottlenecks in building truly intelligent systems.
It has to be the data problem.
The data problem. Specifically, the just sheer difficulty of getting large amounts of labeled action data you needed for training these big predictive world models.
It's the scaling problem in a nutshell, right? We all know world models are key for planning, for generalization, but labeling actions in every single domain it's not feasible.
Which is why the work we're looking at today is so interesting. It kind of takes a massive swing at this.
A massive swing is right. They're learning what's called a latent action model, a LAM, that discovers its own action space.
Just from video.
Purely from video. And not just any video, we're talking huge, unlabeled, in-the-wild data sets.
Okay, so let's be clear about what in the wild means here. We are not talking about, a clean, controlled robotics lab or the set of video games where the actions are all known.
Not at all. We're talking about scaling this to something like YouTube Temporal 1B.
So people dancing, cars merging into traffic, things flying around, just chaos.
Exactly. The action distribution is exponentially richer, which is great for generalization, but the cost is, well, it's huge. You have massive environmental noise.
The camera shake
Or leaves blowing on a tree in the background. Stuff that has dynamics but isn't a meaningful action. And critically, there is no common agent, no single robot, arm, or avatar that appears in every video.
So the real mission here isn't just to learn some latent actions. It's designing a system that can pull meaningful action out of all that noise.
And then regulate it, make sure it generalizes, and actually make it useful for planning. That's the key. Previous LAMs in specific domains, they just didn't have to deal with this level of complexity.
This seems like a good place to jump into the architecture. I think for our listeners, it's probably helpful if we frame the world model using the standard formalism.
Yeah, the setup is what you'd expect. The future state per s plus 1 is predicted by a forward model, let's call it PPSI, and that's conditioned on past states, 0 through free, and the latent action, COT.
Right, so is plus 1 is a function of the past and this STT.
Yeah.
And CST has to capture, both the action and maybe some of that environmental randomness.
It has to try and disentangle them, which is the hard part. So to train this, they have two main components they optimize together. First is the inverse dynamics model, or IDM.
The IDM, that's G-Phi. And it predicts the action, CT, given the current state, and crucially, the next state.
The next state. And that right there introduces what they call a causal leak.
A causal leak, a great term for it. Basically, the model gets a sneak peek at the future to figure out the action that caused it.
Which means the second part, the forward model, that's actually trying to predict the future.
It can just cheat.
It can totally cheat. So the entire technical challenge becomes limiting the information you allow into that latent action state.
You don't want it just encoding the entire next frame, because then you haven't learned anything about dynamics.
Exactly. It's a tightrope walk. You need ZEET to be rich enough, and here it's a 128-dimensional continuous vector. Rich enough to model a car turning, but it has to be penalized, and penalized hard, for just copying the next frame or modeling that tree rustling in the wind.
So architecturally, what's the baseline they're building on?
They're standing on the shoulders of giants here. They use a pre-trained visual encoder, specifically a frozen VJEPA 2L.
So they're not trying to learn visual representations from scratch. They're saying, let's assume VJEPA gives us good enough vision.
Right. They freeze the encoder and let the world model, which is a VTL with ropey embeddings, focus only on the dynamics. The whole thing is trained with teacher forcing on that huge YouTube data set.
Okay, that brings us to the core of the method. How do they walk that tightrope, the regularization?
Yes, and they explore three main ways. Two are continuous, which are sparsity and noise addition, and one is discrete, vector quantization, as a sort of baseline.
The sparsity one sounds really interesting. It's not just a simple L1 penalty, is it?
No, because with a high-dimensional space like this, a simple L1 penalty isn't enough. You can end up with the model just collapsing all the information into a few dimensions.
So what's the fix? They use this. Complex VCM regularization. Covariance mean. What does that actually solve?
So think of the full loss term. It has the L2 part to keep the norms from exploding. It has the L1 part, which you want for sparsity. But then it adds the VCM terms.
Right.
The variance term forces the information to spread out across all 128 dimensions, and the covariance term stops those dimensions from all learning the same thing from becoming correlated. Without it, the model could just stuff everything into 1 or 2 dimensions to get past the L1 penalty. It prevents that dimensional collapse.
A much finer grained level of control.
Right.
And then there's the second continuous approach, noise addition.
Right, and this is more like a VAE, a variational autoencoder.
Yeah.
The regularization here is trying to minimize the KL divergence, the DKL, between your predicted action distribution and a simple Gaussian prior.
So you're basically forcing the learned actions to be a bit noisy, a bit generic, which limits how much information they can carry.
Precisely. You're controlling the information bottleneck by forcing the posterior towards that simple prior.
And then, just for comparison, they use vector quantization.
Yeah, PQ. Forcing the whole thing into a discrete set of codes, which is what you see in a lot of vision language models.
And the initial results on this, they're pretty damning for one of these approaches.
They really are. The sparse and the noisy models, the continuous ones, they do a great job. They can cover the whole spectrum of performance, from a totally unconstrained model down to a purely deterministic one.
But VQ?
VQ struggles. Big time. It stays stuck right down by the deterministic baseline. It just cannot handle the complexity of actions you find in the wild.
So if you're working with natural video, the takeaway is pretty clear.
Continuous constrained actions are essential. The sheer range of movement from a subtle hand gesture to a huge camera pan, it just overwhelms a discrete codebook. You end up with these blurry, blob-like predictions whenever a real action happens.
Yeah, so continuous regularization is the winner. But, just because you get a good prediction score doesn't mean the model isn't still finding some clever way to cheat.
Right. Section 3 of the paper is all about proving the actions are real and transferable. First up, measuring that future leakage.
How do they test that?
It's a really robust protocol. They take a video, and right at the end, they just swap in a few frames from a completely different, unrelated video.
Yeah.
An abrupt scene change.
And if the model was cheating, if SIST was just an encoding of the future?
The prediction error wouldn't change much, but that's not what happens.
What do the numbers show?
Across all the high-capacity models, the prediction error measured in LPIPS more than doubles. We're talking a 2.3 to 2.5 times increase in error when that scene change happens.
So that's pretty definitive proof. The latent actions are not cheating.
Not in any significant way. And actually, the complexity of the YouTube dataset probably helps here. It makes it much harder for the model to find a simple cheating solution than it would in, say, a simple video game.
Okay, so leakage is out. Next, you have to prove the actions are actually transferable. That ZT is a meaningful, reusable idea.
This is where they use the cycle consistency test. It's a really elegant idea.
Walk us through it.
You take two videos, A and B. You infer the action, Z, from a transition in video A. Then you apply that action Z to video B to predict a new state.
Okay, so you're transferring the motion.
Exactly. Then, from that new predicted state in video B, you infer the reverse action, call it Z prime. And you apply Z prime back to the original video A.
And if Z is a real general concept of motion, then the final state in video A should be pretty close to the original.
The error increase should be minimal, and that's exactly what they found. The prediction error only goes up by a factor of like 1.14 to 1.34. It shows really high transferability, even on totally different data sets like kinetics and recon.
So you can literally take the motion of a man walking and apply it to a flying ball.
And it works. It validates that these latent actions are true abstractions, not tied to the specific objects in the video they came from.
Which brings up the biggest question of all, embodiment. If there's no fixed robot or avatar, what is actually representing? What is the model learning?
And this, I think, is the most profound part of the paper for anyone thinking about general AI. Because there's no common embodiment, the model is forced to learn actions that are, and this is their term, spatially localized and camera relative.
Okay, what does that mean in practice?
It means the action isn't person walks. The action is an instruction tied to a specific patch of the screen, a specific location, and a motion vector relative to the camera's point of view.
So it's completely abstracting away the semantic identity of the object. It doesn't care if it's a person or a car.
Exactly. It just cares about the kinematic primitive in that spatial region. And that abstraction is what makes the transfer possible. The agent action becomes a spatial dynamic.
That's a huge shift in thinking.
Yeah.
And it sets up the final piece perfectly, using these generalized actions as a universal planning interface.
Right. The whole idea is you can take this general world model trained on everything, and then for a specific task, you just train a small domain-specific controller.
A controller, a full, that maps your real robot actions, let's say, to the learned latent action Z.
Yes, and they point out that this controller needs to be conditioned on past representations, not just the current state.
Why is that so important?
Because if Z's is camera relative, the controller needs that history, that context to figure out how a desired absolute action, like move forward 1 meter, translates into the correct relative latent action for the current camera frame.
That makes sense. So they test this whole setup for planning on 2 different tasks.
They do. They use Droid for robotic manipulation and recon for navigation, and they use the cross-entropy method, CEM, for the actual planning.
And this is where we get the big, non-intuitive result.
Yeah, this is the core finding of the paper, really. The model with the lowest prediction error on the YouTube videos.
The one that's best at predicting the future visually.
It is not the one with the best planning performance.
That seems backwards.
It does, but it makes sense when you think about it. The best performance comes from a model with a middle ground capacity for Z.
So too much constraint is bad, but too little is also bad.
Exactly. If Z is over-constrained, it just can't represent the complex actions you need for a real robotics task. But if it's under-constrained, it's carrying too much junk information, all that background noise and stochasticity. The planner ends up trying to plan based on noise.
But hold on. If the rollouts, the visual predictions, look worse or noisier for these middle ground models, how can you trust their internal representation for planning? Doesn't that undermine the whole idea of a predictive world model?
This really gets at a known challenge in this field, this decoupling of visual fidelity and actual task utility.
Yeah.
When you look at the raw planning performance on the Droid task, their model is comparable to VJEPA 2AC.
Which is a strong baseline trained on in-domain action-labeled data.
A very strong baseline. And on the recon navigation task, they're competitive with non-world model approaches like Nomad.
So the performance is there, but the decoupling is real.
It is. The models using noisy latent actions, the VAE-like ones, often get the best planning results, even though their visual rollouts can be blurry. It suggests that the regularization forces the model to learn a coarse but very useful representation of dynamics that's good enough for the CEM planner, even if it's not good enough for a perfect pixel-level prediction.
Task completion over visual realism.
That's the trade-off.
Let's touch on the scaling trends before we wrap up. For people looking to build on this, what happens when you just throw more resources at it? More model size, more data, more training time?
So all three, as you'd expect, make the inverse dynamics model better at its job on the natural videos. The model gets better at predicting zit.
But what about the downstream task? The planning.
That's the interesting part. Only one of those three increased training time gives you significant, consistent improvements in planning performance.
So just making the model bigger or feeding it more YouTube clips has diminishing returns for the actual task.
For planning, yes. The interpretation seems to be that given how incredibly complex this latent space is, the model just needs time. It needs time to really learn the dynamics and separate the agent's action from all the environmental noise. More size and data help the IDM, but more time refines the utility of what it's learned.
So to sum this all up, this is a really successful demonstration that you can learn a general, continuous, latent action world model just from unlabeled video.
Absolutely. And the key innovation is that continuous regularization, either the sparsity with VCM or the noise addition with DKL. That's what manages the information flow.
And that leads you to these transferable, spatially localized actions that can work as a universal interface for planning.
Right. And the authors point to some cool future directions, like having the model adapt its information constraints based on how complex a video is, or maybe even integrating the LAM training directly into the VJPA pre-training.
All important steps. Yeah. But if we bring it back to that core finding, the fact that the visually uglier models planned better, it really does raise a provocative question for you, the listener, to think about.
Given this result, how much longer should we be optimizing for photorealistic video generation, for high-fidelity rollouts, versus optimizing purely for task utility and better planning, especially as we start to deploy these kinds of general AI systems in the real world?